I'm Briggs. Time for another episode of Uncertainty and Probability Theory, the Logic of Science. Repairs are still being made on the shack, so we're stuck with this whiteboard, which of course I light very badly, but I don't think we need it much today. At least I hope we don't need it much today. I figured out how to insert graphics into the videos, so I'm going to insert a couple of graphics. Now, what we're going to do today is, last time we talked about the philosophy of models, and we're going to review that briefly. And then we're going to talk about, and that was the right way to do things. And we went over a particular model, and we did that particular model in the right way, or at least a right way. We did learn this. For whatever, if we're talking about science in particular, or anything, we talk about some proposition of interest that we have. If we can identify the full cause, the cause of it, meaning the explanation for it, the reason for its existence, its nature, its essence, and the final, formal, material, efficient causes, and the conditions under which these causes are brought about to create this thing, then we have a model, a perfect model, an objective model, a model that tells us everything we want to know about our proposition of interest. Not correlational at all, and we're confident of saying we know the cause of these things. Those type of models are extraordinarily rare in science. Basically, we have models that encapsulate some areas of causality, some pieces of causality, but not full cause. We learned very important things about that. And so we'll cover that in a second, but what we're going to do today is a way, I try to emphasize this A here, you probably can't even see it, a way of doing modeling wrong. There's an infinite number of ways that you could go wrong in human thought, so I'm not going to be able to cover them all in this brief lecture. We are going to cover, however, a very common way of going wrong, a way of thinking wrong. So let's review a little bit more about the idea. So we have whatever we want, and I've talked about this many times. We have some proposition of interest, and I'm going to call it Y. Just it's going to be some proposition. It doesn't matter if it's a mathematical proposition, it's a proposition about measurable things in the world, or it's an entirely fanciful proposition. I'm trying to keep my computer awake here. I got to set that thing again. It doesn't matter what it is. It's what we want to know about. This is what everything we want to know. Last week we used the GPA, the first year GPA of college students at a particular college. I can't even remember what the college was. There's links to it. You can download the code and download the data, all that kind of stuff. But whatever it is, we have some proposition. Usually, if it's science, we're talking about something measurable in the world. We want to know the truth of something. But not always. It doesn't have to be. I mean, numbers are not in the world. They're certainly not in the world. Numbers are not something. There are numbered things. There are numbers of things, but numbers themselves don't exist in the world. They're not physical creations, which is very strange because now most mathematicians even agree with this kind of a thing, yet somehow they view probability as being in the world. So we have to talk about that a little bit. So we have Y. Now we're going to gather X, which is all. Oh boy, I think I have another one here. All, every, all, A-L-L, everything that we think is relevant to Y, or that we can get our hands on, or that we know about Y, or willing to consider about Y. It's going to be a very long proposition usually, enormously long sometimes. Was filled with deductions and implicit and tacit premises and all the way. But in any case, we gather our data. For the particular data that we used last week, the GPA, we had some, I don't know how long it was, some time period in the past. There was a couple of hundred observations, and we picked a model for this. We decided we were going to pick a model for this. We used a normal model, a normal distribution model, to characterize our uncertainty of GPAs not yet made known to us or not yet used to us in this thing. And we learned that for any model, any proposition of interest Y, any data, all we had to do is then form this. And this is the model. And in fact, we learned all modeling is nothing but probability. This doesn't matter if you're in physics doing quantum mechanics, or cosmology, investigating what you think might be dark matter or whatever, or in medicine, investigating cures of diseases or genetic structure, or chemists looking at protein bonds or something like this, whatever. All models are like this, absolutely like this. And since X may or may not be in the world partially or fully, and Y may or may not be in the world partially or fully, the probability is nowhere in the world. The probability is in your mind. The probability, and your mind is not in the world. Your mind is a non-material thing. The rationing, reasoning intellect that we have and our wills are not material. Now, I know that goes against some scientific precepts, which says everything is just atoms bumping into each other and so forth, but I don't hold with that. And so therefore, I don't hold with probability being in the world. So all models are just this, nothing more than this. We learned that modeling is just probability. So that's really what we're done. We learned all about probability. We spent, well, this is 67. We spent 60 plus lectures justifying this interpretation of probability. It took over a year. I'm sure it was tedious to a lot of people, but we finally arrived at this point. Now we're doing models, and we learned that models are nothing but probability. For the GPA one, we had GPA equaled some value, whatever it was. We had our data in here, which is, this is all our X. We had normal. We picked a normal with its parameterizations. We had to pick a parameterization, which I'll remind us of in a moment here. We had the method of integration that we used to figure out the math of this thing, because this math is integrals and so forth, because the normal distribution lives on the continuum, so we're doing these integrals and so forth. And it turns out we need to use integration to do this. We had a method of integration, it's this MC stuff. And that's it. That's it. That's what our model was. We learned that this particular thing, the probability that any GPA unknown to us or not used by us will equal G equals 0 if we're using the normal. So we had to find some way of discretizing this, because all actual GPAs we can ever measure will only be finite and belonging to some discrete set. Even if the discrete set is very large, we went over all that, it'll still be finite and discrete. So this probability will always be greater or equal to 0. And of course, it'll be less than or equal to 1, depending on the GPA and so forth. But that's it. So that's everything we had. Now here's a little thing. So we had data. We had n observations in here. This right here, we'll just call this our x n normal. That's our x. X equals this. X n normal, whatever we want to call it. And here's our y. This is our y. So we have the probability of y given x n normal. There's our model right there, if you can see that. Probability. I'm going to have, obviously, the write-up has all this stuff in there. You can look at all this stuff up. Now, if I suppose I go in here and I find one data point is bad, or I add a new one. Even more common, I add a new one. I could take one out, I could put one in. It's one of these observations, and I keep everything else the same. Everything else the same. Of course, the integration would change, but we'll come to that in a second. That would be, I'll call that x n plus 1 normal, by adding that extra data point. And then we have the probability that y given x n does not necessarily equal the probability of y given x n plus 1, except accidentally. Except accidentally, by coincidentally, I mean to say. Of course, two probabilities can equal each other. Coincidence, you can have the probability of some weird random shuffling, random shuffling of a deck of cards equaling the probability of some dice throw just by the circumstances that you set up, but there's no causal relation between the two. So that's the case, and this is not a bug. This is not a bug. Of course, if we change the data point, we have to do our integration. We have to reintegrate. If we're using the standard cheesy methods that we have, because a lot of these things are not analytic, we'll come up with a new set of data points that we use in the integration. So those will change too. So that's implicit in this xn plus 1. And then the probabilities won't match. There is the expectation, though, that people have that the probabilities should match. the probabilities should match, or they should converge, or something like this. Nothing that's just not true. It's absolutely not true. You change the evidence, you change the evidence, you change the evidence, you change the evidence, you change the probability. Unless you're adding or subtracting something that is not probative of y in the face of whatever you have considered up to that point. We did all that kind of stuff in probability 4. Now you can see how it comes back into models. I'm going to state it all again because it's extremely important. If we change any of this, any of it, we add a data point, we subtract a data point, we change our integration method, we carry our integration step 10 steps further into the future, which means we add 10 more of these uniform, supposedly uniform numbers and so forth. We change the probability. Any change at all that's probative of y changes the probability. Of course, we can add a truth to this. We just add a truth, you know, like A equals A, proposition A equals A, or A is identical to A. That's a truth. That's not changing anything because it's not probative of y in the face of x. Whatever we have in x, if we remove from x, we can change the probability of y. We add to x as long as it's probative of y, we change the probability of y. That's probability. Probability doesn't adhere in y or in any of this other stuff, so there is no correct probability. There is no correct model. And therefore, not all models are wrong. All models are exactly what models are. They're this. All models are this. This is not wrong, except in the very arcane sense that unless x is not the full cause, in the way we discussed before, and the conditions. And so we don't have extreme probabilities. In other words, this doesn't equal 0 or it doesn't equal 1. If the model is any one of those and it just lives in 0 to 1, where the parentheses and not brackets, if you know that much math, then the model's not wrong. You hear some people say, this guy named George Box said something like, you know, all models are wrong, but some are useful. No, all models are correct in a more broad sense, but whether or not they're useful, that's an entirely different thing. So I can't emphasize that enough. That's how to do modeling right, and we're going to learn that over and over and over as we go through a whole suite of class of models. But I see I've gone too far and too much again, so let's now do it the wrong way. So let's remember that in our normal model, well, I'll erase all this. I guess we don't need it. This board, okay. We had a normal model, which is, you know, the bell-shaped curve. We know that's strictly wrong. We know it's wrong because that gives positive probability to every possible GPA from minus infinity to infinity. And GPA, in our particular example, GPA can live between 0 and 4.15. That's just the rules of the game. Nothing outside the case. And we did our model. We did it for whites and non-whites. We had two things. I can't remember the exact picture, but it was something like this. These things should be symmetric. Let's see, my artistic abilities is why I became a mathematician. These should have the, because we set this, so I'll remind ourselves in a second. We got certain probability. We got like 2%, was it? Something like this, 2% chance of being larger than 4.15 in the model. The probability of GPA, given all that stuff we had, the normal model, all that kind of the data we had and so forth. We got like 2% chance of being greater than 4.15 for whites. And there was like a 1 in 1,000 chance for non-whites. The non-whites had a bigger chance of being less than 0. So is that we know the normal approximation was going to be wrong. And the question then becomes, which we did not answer, we will not answer today, is that big enough to make a difference? Difference in what? There's no universal, necessary, absolute, true way to answer that question. Just isn't. Is it useful to you? I don't know. Is it useful to a college administrator? I don't know. Is that much error going to play? Who knows? It's up to decision. We're going to learn how to do all that in a more formal way later on, but that's the decision that people would have to make. Okay, I have my Japanese marker here. Okay, Pentel. Okay. All right. What was I going to talk about? Ah, yes. So we had the normal model. We decided that we'd have one parameter, a central parameter for whites. Call it, because the normal has to have two parameters. It tells you where it lives, the center, and amount of spread. And we had a normal parameter, a central parameter for non-whites. And then we had a spread parameter, which we let be the same for both. And then we did our thing, and we calculated, this is GPA, of course, this is the probability of new GPAs, and we discretized this into buckets. Those discretization buckets depend on the uses you're going to, there's no one correct way to put the discrete bucket in there. In other words, you could look at GPA every single unit. I could carve up the probability from 0 to 1 and 1 to 2, 2 to 3, and that could be crude as it is, useful enough for me for whatever purposes I have. Or I could do it every half a GPA point, 0 to 0.5, 0.5 to 1, or I could do it every 10th. Whatever I'm going to do, it's up to me. I could discretize however I'm going to calculate these probabilities, because we have to do something, because we know the normal is not a correct model, in the sense that it's not a wrong model, it's just an approximation. We know it's an approximation because GPA lives only between 0 and 4.15. I called this kind of stuff over here probability leakage. Given the known facts we have about GPA, if we have probability for impossible events, that's probability leaking outside of our model. Okay. And interestingly about this model can't be falsified. I should have brought that up before. This model cannot be falsified. I get a probability right here. I can't remember what it is. Say it's 1% chance for of 5 or greater or something, or greater. A GPA of 5 or greater, which is impossible. But the model has made a prediction of something that could happen. Give it positive probability. We'll never measure a 5, but there's no way you could falsify that based on observations. The model can't be falsified. This model is only made inappropriate because of our outside information, because of our rules of the game. In effect, we could say we have falsified the model, not by the observations, but by that it gives positive probability to stuff that cannot happen. Okay, that's a digression. It can't be falsified by the observations, because 4.15 will not falsify the prediction of 5, nor will someone coming in with a GPA of 0 falsify a prediction of a negative GPA. It just doesn't work that way. That's not how falsification works. We could say the model is just not that good because it gives us positive probability for events we know are impossible based on other information not inside the model. All right, that's the probability leakage. Now, because of all this, we know that there is no such thing as true values of these parameters. There is no such thing as true values of these parameters. First of all, nothing lives on the continuum. And even if it did, some things you might say, well, what about space is absolutely continuous or something? Oh, okay, maybe that's a good point. We could think about how we model space and so forth. So maybe that's absolutely true in those cases. But in this case, we know these parameters do not exist. They don't have true values. So it doesn't make sense to speak of true values, right? Because they're only approximate in any sense. But we could still use them in a model to make approximations. For instance, I could say I have a die that has, my model of the die has 7 states. 7 states. A real die has 6. I'm going to give the probability of being less than 6 in this model. This is a model of being a probability of a roll less than or equal to 6, given this model. Given this model here, will be 6/7. In a real die, with a different assumption, the roll less than or equal to 6, given we have a model with 6 states. Here's a different one. This equals the probability of a roll being less than or equal to 6 equals 1. This model here is still it could be a reasonable approximation for this model, depending on what you're doing. If you're trying to make money out of it, maybe not. But if you're trying to just make it an illustration or something, this model still fits this situation to a certain extent. But we know that none of this stuff, it doesn't exist. There's no die with 7 states in this particular case. Okay. All right, so I've already blown 20 minutes. Okay, I'm sorry about that. I know I should go quicker, but you guys got to tell me. There's so much material to cover here, and I've already, blown through 68 of these lectures and taken 1.5 years of your time. And we're just now getting to the stuff that you guys want to know about. But I had to tie it all together. It was my duty, I felt, because I'm making statements like this. And in order to justify those statements, I have to work backwards. We always have to work backwards in any kind of logic or math or probability to first principles. And then we did those first principles. We relied on our intellects. Our intellects, the most sure form of knowledge that we have, a certain form of induction that we use with our intellects. There's no more certain knowledge, a kind of faith that we all have. And we built from that all this stuff, and we moved to this thing. So we could justify every step that we're making in these models all the way back to the beginning, which is not, that you see, in the wrong way, which is what we're going to learn a wrong way we're going to learn now. After all these digressions, which I should just shut up, I can see I'm going to go 45 minutes again. Okay, I am going to insert here. So what we do, basically, in a wrong way, is we forget about this question. We wanted to know about the probability of GPA. We knew about everything about the past. We did not need to do probability models to say anything about the past, because we knew all about the past, all right? So we wanted to know how many people got a GPA greater than 3 and they were white or non-white. We just go and look and count. That's it. Done. Everything we knew. So we only are interested in stating uncertainty of things we have not yet been made known to us. Usually it's newer in the future, and sometimes I fall into the habit of saying that, but it's not necessarily so. It could even be data that's known to me but not known to the model. So data that's not yet been accounted for. That's a long way to, a lot of words, so I end up saying new, but we must always remember that's what I mean by it. Okay. We wanted to know about GPA. We wanted to know the probability GPA was greater or lesser than whatever numbers we wanted to pick, or we wanted to know the probability that whites had higher GPAs than non-whites, or lower GPAs than non-whites, or whatever we wanted to know. We could ask any question we wanted of this model. What's the probability whites will score greater than 1, and what's the probability non-whites will score greater than 1, or in some interval between 1 and 1.5. Whatever we wanted, we could answer with this model. We're going to throw this question out now, and we're going to say, hey, aren't these parameters neat? Look at all this nifty math. Wow, we got some math we can play with here. Let's concentrate on the math. Now what we're going to do is we're going to form estimates, a very bizarre word in this case. I'm running out of ink and all these things. I know I have some more here somewhere. I'm not certain of the color of this thing. I hope it shows up. And I'll put a question mark over it. I don't know if you can see it. Statisticians and others, econometricians and so forth, are in the habit of putting these little hats, they call them hats, over these things here to indicate that we have made an estimate of them. And I got the numbers here. I should have memorized them. I kind of did, but how can we estimate something that doesn't exist? We cannot. There are no such things as estimating things that do not exist. However, we can come up with numbers for these, and that's what we're going to see here. I'm going to put the table in here. I hope you can see this table here. This is done by getting the software in the same way we did last week. Here is a table that comes out, and you'll see it. Here's the formula that we typed in to get the code, the software, and up will pop the answer. We'll see it'll say something like intercept, and it'll say white. And it'll have the parameters. Make sure I got this stuff here. 2.84.32. 2.84, 3.2. And there'll be a column way over on the right, which would be our p-value, 10 to the minus 16 and 10 to the minus 5. 10 to the minus 16, and for us, close enough, 10 to the minus 5. It's called intercept for whatever reason. There's good reason for it. It's just coding practice. This is the non-whites. This is one of these quirks of coding. Yeah, every piece of software is different, and you have to memorize how the software works and what it says and so forth. We have a category here, whites and non-whites, and so this has to be non-white. The white is here, so this is non-whites. And there's more to it we'll learn later, but that's for all we need to know right now. So they say the model is going to give us an estimate of 2.84 for this thing here. And here is 0.32, excuse me, 0.32 for whites. And it's not this parameter for whites. What they instead give us is the difference. This is the difference between whites and non-whites is the parameter here. And that's just another software quirk. And there's a good mathematical reason for it too, which we'll cover in the future and so forth. But it doesn't matter. For our purposes, it doesn't matter here. So this, we might say for the whites is, what is it, 3.1, 3.14, 3.16, okay, something like this. All right, and here we look at that table. If we go back and look at that table, we wanted to know this so we could draw. We can't draw the picture, even if we absolutely, even if per impossible, these things really had true values and we really estimated them perfectly correctly. We can't draw this picture. We can't say anything about the probability of GPA unless we know what this is. And the software doesn't, by native happenstance, it doesn't show you this number because everybody has forgotten about this question by now and they're concentrating on these things right here. They're thinking, whoa! And now you can see kind of the difference. These parameters, and I'll show you why they're concentrating on them, and it's for a very bad reason. And the reason is this. Now we're going to do our hypothesis test. We learned last week the hypothesis was, are whites different than non-whites? And the answer was, without even looking at the data, yes. Otherwise, we wouldn't be able to characterize whites and non-whites. Okay, so that was our first hypothesis test. Our second hypothesis test, which we got from looking at the data, we say, were whites different than non-whites? The answer was yes. By looking at the data, they weren't the same. So there's differences. So with a probability of 100%, given that we saw the differences, the probability there are differences is 100%. There's our probability. Our hypothesis test has been passed and so forth, but that's not the magic value. That's not the p-value. We need to get a p-value out of this. And remember, we said nothing about cause. We said in that particular data, we had the whites scoring, there were several more scoring higher than non-whites, and there were some non-whites at the bottom, and they had a lot fewer of them, and they had a little bit bigger spread around. What caused that? I don't know. There's 200 some people in this data set. Maybe a third of them were non-whites. Every single person has a whole range of causes that led to their GPA being whatever it was. They had different numbers of classes, different complexity in the class load, and on and on and on. But if you wanted, you could have said, hey, it's whites being racist toward non-whites. And so the whites subtly move themselves ahead, even of the Asians who belong into the non-white category. Why not? Or you could say, and that's why the non-whites didn't score as well. Or you could say, which no academic would say, that the whites are more intellectually equipped. Not for racist reasons, but because of innate reasons. Whites are just intellectually superior to non-whites. And that's what, and it takes intellectual effort to get a GPA, therefore that explains why GPAs were slightly higher for most of the whites. Both of those hypotheses, and an infinite number of other hypotheses, causal hypotheses, are possible in explaining this data. Because remember, we did this back, I don't even remember, 20 lectures ago, something like that, or more. There's always an infinite, remember we're doing all those things, we did a lot of people got angry at these. I gave series, 1, 1, 3, 3, 1, 1, 2, 2, 3, 3, and then asked you what the next numbers were going to be, and it turns out to be 5, 5, and not 3, 3, because there's an infinite number of possible series that explain the first data that we have. an infinite number of causal theories that we could fit into there. And I gave you some legitimate ones taken from this math. There's a site of series, I guess it's called, or something. I'll give you the link for it. I can't remember the name of the thing. So in this thing right there, we don't know what the cause is. All we see is the data. There's no number we can extract from this thing to give us an indication which of these causes are correct, of the ones that we're willing to entertain. Equally likely to be racism or intellectual superiority or any of a number of other things. So finally comes to our hypothesis test. Already 30 minutes. I apologize. I really do apologize. I really wanted this to be less. The hypothesis test, remember we did p-values before, is that this parameter without the hats, this difference equals 0, which is another way of saying this thing, non-whites. The white central parameter equals that don't exist anyway. These parameters we already know don't exist, but it doesn't matter. Probability we can talk about unicorns in probability. It doesn't make any difference. So the hypothesis test, the null hypothesis, is that these two parameters are equal to one another. And we, by design, said that the spread was equal to one another. We just assumed that. That's the case. We conduct, and you'll see down in that table, if you go back and look, there was a t. I forgot what, I'll go back, I can glance. There was a t statistic in there because this is a t-test. They did a t-test, and they got the p-value, which is this, which is much less than the magic number. Much less than the magic number. You remember the magic number. I'm never going to remind you of the particular value again. So we are now entitled to say that this is not true, that these parameters are not equal. And therefore, when we come to write our peer-reviewed paper in the discussion section, we are free to say whites are racist against non-whites, because that's information that we say is backs up our cause, our causal hypothesis. We reject this hypothesis here. This is a hypothesis, a proposition, that this parameter equals this parameter. We reject it, therefore we deduce that they do not equal one another, and they say they are different. All right? So none of that makes any sense when these parameters don't exist, okay? None of this makes any sense at all, but we do this p-value. We know the p-value has nothing to do with any kind of causal hypothesis or anything like this. We know, we proved out, I don't know how many lectures on that. We're all nauseated by that, but this is exactly how people do things. They now reject this null hypothesis. They say race is linked to GPA, or race is associated with GPA, or white racism is associated with lower GPAs for non-whites. We could spin that story out an infinite number of ways, but we could spin any story out an infinite number of ways. We haven't done anything here, and we don't even know what this is. We can't draw this picture. We've forgotten this. So the next step is what people do, and I ask you to believe me. I have to erase my. Let me get this one a little bit better. I have to erase this picture here. As they say, well, is this 2.84 the exact value of the theta non-white? And is this 0.32 the exact value of the difference between the theta white and the theta non-white? Well, they say, no, there could be small, we're not 100% sure these estimates are correct. So they do a confidence interval. And I'm going to show you, here's where I'm putting in the confidence interval. I'm waving my hands here, so I'll make a note for myself, 34 minutes, so I remember where to put the thing in. I'm very bad at this video stuff, as you can tell. I should find ways to learn about this, but it takes a lot of time, and I'm lazy and inefficient with this stuff, as you can plainly see. Okay, so they do a confidence interval, and let me get the numbers here. I gotta cheat because I haven't memorized this. There'll be a table, and it'll have the code that you get it there, and it'll have that intercept again, the intercept business, and then the white just as the same as we had before. And you'll see a 2.5% and a 97.5%, and the number is something like, I'm going to just do these quickly, 175, 2.97.466, something like this. And the difference between the 2.5% and the 97.5% is 95%. So we're going to call this a 95% confidence interval. Now, what's the most natural thing to think in the world? We just said, well, there's a 95% confidence that the parameter theta NW is between 2.71 and 2.97. That's perfectly correct, as long as we interpret confidence not as probability, not as anything. We did confidence intervals before. These are the most bizarre creations in the world, because the interpretation is this. The interpretation is this. We did this before. If I were to repeat the experiment that gave rise to the numbers, the 200-some numbers that we had, the students that we had, the 200-some students we had, and it was exactly the same. The experiment was exactly the same, but randomly different. And I ran that experiment an infinite number of times. An infinite number of times. Not 100,000, not a million, not a billion. Infinite number of times. And each time I computed the confidence interval. I did the whole thing. I repeated the experiment exactly the same, but it was randomly different, because don't forget, in this view of the world, probability is real. Probability is causal. Probability is pushing things hither and thither. Then 95% of those intervals, not this one, forget this one, then 95% of those intervals that I calculated will contain the true value of the parameters. All right? Again, I do the experiment an infinite number of times. Each time I create the confidence interval, compute the confidence interval, and 95% of those intervals will cover the true value, or will contain the true value of the parameters. What about our particular confidence interval? The only thing we're allowed to say is that our true value either lies inside this interval or it doesn't, which is a tautology. From minus infinity to minus 17 is a confidence interval I can write down, and it's absolutely true. Even if parameters had true values, that it's absolutely perfectly true that the true value lies in this interval or it doesn't. Even if we know the parameter has to be positive. You could say that for any interval. So what do people do with these confidence intervals? When they don't even have to calculate them, they say nothing about any real life confidence or probability. You must not say there's a 95% chance that the parameter's in there. If the interval is wider, you must not say there's less of a chance that our probability is covering the value. You can't say anything about this stuff, yet people still do it. Why? It's madness. It's madness. They can't maintain any kind of consistency with these things. And instead, they interpret it like a Bayesian would. And then we'll learn how to do the Bayesian analysis probably next time. They interpret this stuff like a Bayesian would, and we'll get into that, which is forbidden in frequentist theory. But everybody does it, without exception. You'll see some enlightened authors, they see some criticism like mine and so forth about p-values, and it kind of stings them a little bit. I'm not the only one making these criticisms, and I'm by far from the first one making them. They were made from the very beginning, but including most presciently by Harold Jeffreys, a physicist naturally. But you know, over 100 years ago, or was it 100 years ago? So this is a long string of people making these sane and sober objections to p-values and so forth. And so these editors of journals will say, you know what? They might be right. You know, maybe p-values should be, maybe they should be eliminated. Well, we'll not require them anymore, or at least we'll not emphasize them anymore, because we certainly know that just because the p is we haven't proven cause. That's true. We know we haven't proven cause. But we'll replace them by confidence intervals instead, because that's giving us more information. That's giving us more about the uncertainty we have in the parameters and so forth, which is just as wrong, just as flawed. And you'll notice that these confidence intervals and the p-values, as we talked about before, mathematically, they're not one-to-one mathematically, or you get exactly the same thing, but the results are the same, one-to-one. That is to say, when the p-value is the confidence interval won't contain, this in particular won't contain 0 and all that kind of stuff, which we'll talk about more in the future and so forth. So there's no way of remaining coherent when you talk about estimates, first of all, for things that we know don't exist. You can't, it's like estimating Bigfoot's height. What's the true value of the mean of Bigfoot's? All right, what's the true? Of course, now I'm going to have a lot of people saying, okay, well, there's Bigfoot's. All right, so now we need to have something that people think doesn't exist for sure. A happy feminist. Okay, so we want to have a happy feminist. We want to have the average height of a happy feminist or something. Okay, so these creatures don't exist. So there's no sense pointing at getting an estimate for getting the true estimate for things that don't exist. Okay, so there's no point doing estimates. There's no point then doing confidence that we have in our estimate, especially when the confidence doesn't mean anything close to the English confidence. And there's no point doing p-values, which tell us nothing about the probability of GPA. And we've forgotten in all this stuff that our whole point was to say something about the probability of GPA, and given whether a person was white or non-white. That's what we did last week. We could have just did that. And we could have said, yeah, the normal's not so great, but whatever, 1%, 2% probability leakage, it's nothing for my particular purposes. I don't care about 2% leakage, and there we go. It doesn't tell us about the causal differences and so forth, but it points to where I can go and look for causal differences if I want to then set up an experiment and so forth, which brings up the idea of control. There were, in fact, in this data set, more things besides race, white or non-white. There was, I can't remember. I have to go and peek. There was like hours. I'm making this up because I can't remember. It's what was your SAT score, or how many hours did you spend studying, or how many STEM courses did you take, or something like this. So there's more information that each kid had on his GPA. And we can incorporate that stuff into the models, and next week we will. We'll incorporate that in the model. We'll do it the right way, maybe the right and the wrong way together before we get to the Bayesian interpretation. The Bayesian interpretation is just as wrong, but it's a little closer to being correct. I don't want to say that. I wish I didn't say that. It's a little closer to being correct because this gives a saner view of what these intervals are, a saner picture of what these intervals are, but it still speaks of estimates of non-true, estimating things true value when we know they don't exist. So they don't meet that kind of thing. So we'll do the right way. The right way was just probability. The right way was just probability. We'll do probability and the wrong way too. What we're going to do in probability is we're going to calculate the probability of GPA, given all that stuff plus race. I can't remember what was in there, like SAT scores and number of STEM classes, whatever it was. And all the other stuff. That's all. We'll just calculate it that way. Right? No problem. We can do it anyway. We can ask any question we want in probability. We can calculate the probability for it. Why don't we just do this instead of all this rigmarole? This is a question I can't get people to answer. I can show them all this stuff and I can wave my arms around like a maniac, like I'm doing to you for a year and a half, and I can't get anybody to answer this question. Why don't you just do this? Why don't you just do this? They know how to do this. The math comes out. It's all there anyway. You can get these answers. Why not just do it? I don't know. But the wrong way is to say we have controlled for these things. This is one of the other. Estimates are a fiction. I'll put it this way. Which is an understandable fiction if you believe probability really exists in the world. But this is a lie. You're not controlling for anything. It's not that you designed an experiment, like I've said this a million times too, like a chemist would. You want the control, the pressure in the room, the heat, especially if you're looking for added heat to some process or something like this. You are going to control for every possible known way that heat can get in there. And you may have missed things. That's how experiments go bad. That's real control, or at least an attempt at real control. This is just throwing crap into a regression, but it's called control. and it leads to any number of misleading ways of thinking about things and over certainty. All right, well, the other one was 45 minutes. This is 45 minutes, and I only covered just a bare fraction of this. Please bear with me. Let me know how you're thinking about all this is going in the comments and so forth. And that's it for now. WMBriggs.com, WMBriggs, Substack.com. That's the bigger one. Thanks for watching.